Good afternoon. I hope everybody is enjoying the afternoon of day 2 of Google Next, Cloud Next. This afternoon, we're going to talk about storage, and in particular, how to really use Google Cloud Storage to optimize for your different workloads. We'll talk about content serving and delivery. We'll talk about data analytics. We'll talk about how to really optimize and use storage classes, performance, and optimize for scale. So that's our agenda today, and let's go ahead and get started. So let me start out by talking a little bit about Google Cloud Storage, GCS, and what it's able to do for you. GCS really is the foundation for most cloud applications, providing a very powerful set of constructs for storing object-based data. When we look at GCS, a lot of the power really comes from the fact that it provides a unified experience. A single API for your hot data, your cold data, your ice-cold data, and archival data. A consistent set of performance characteristics, so you get fast access to hot or cold data. So it's very consistent across the board. Single API, single performance profile. One of the unique features of Google Cloud Storage is it provides consistent listing, meaning when you write a piece of data, you get that data is immediately accessible to you from your applications. This makes GCS particularly well-suited for Hadoop and analytics workloads. Analytics workloads that really require very fast access to data as it's writing. GCS is also geo-redundant, taking advantage of the power of Google's global network to be able to give you access to your data in a region across multiple regions. So very fast access to data, replication for the most mission-critical workloads or most sensitive disaster recovery scenarios. And then it is scalable to exabytes, right? I'm often asked, can I create lots of buckets? Absolutely. Can I create lots of data? Absolutely, right? GCS gives you that infinite storage in the cloud that you've always been looking for, and you can structure your data any way you want in order to take advantage of all of that capability. Underneath GCS is the power of Google's global network. Over 100 access points around the world and growing, dedicated undersea cables that give us transcontinental and cross-continental access, gives you the ability to move data around quickly, especially if you're trying to do multi-regional and global data management. Now, the power of GCS really makes it well-suited for a variety of different applications. Whether it's content storage and delivery, the ability to store your data and serve it to the public or serve it to other applications, stream data, stream audio, you can really take advantage of GCS, the Google Global Network, our edge caching, to really deliver that data anywhere you want. It's also very well-suited for data analytics and ML. Consistent listing capabilities ensure that your applications can simply use GCS as if it were a consistent storage system and run at full speed. And then, of course, archival. For your coldest data, the data that you want to protect, we've introduced features like bucket lock that allow you to guarantee that your data is being retained and then guarantee that your data gets deleted after the retention period is over. So long-term storage in the cloud that's safe, secure, and managed. So let's spend a little bit of time talking about how you can use GCS to really support all of these different types of use cases. Storage classes have a way of describing a bucket or a collection of data, and each storage class is a combination of a location and a hotness or coldness, right? And you're going to basically, as you create a bucket or define an object in GCS, you choose your storage class based on the workload, the location constraints, and how you plan to access that data. So this table summarizes how GCS really gives you access, right? We have two axes, a hotness axis, so we have standard, nearline, and cold line as different levels of access, and they're priced based on the amount of data you're storing and your access pattern. And then we have three types of locations. regional locations, multi-regional locations, and dual regional locations, which really define how your data is replicated across Google's network to give you disaster recovery and redundancy. So let's talk a little bit more about these different locations. Right? Your locations, as I mentioned, are regional, multi-regional, and dual regional. Right? Our regional locations are located around the world. They comprise multiple zones in a single area. Multi-regional are continental locations. So we have a multi-region in the United States, a multi-region in Europe, a multi-region in Asia. And data is guaranteed to be replicated to at least 2 regions within that multi-regional location. Dual regional data is data that is guaranteed to be replicated between 2 specific regions. And we have a multi-region in Europe and a dual region in Europe and a dual region in the United States. So this gives you location certainty as well as geo-redundant replication. So let's kind of explore that a little bit more. Right? With regional data, very much optimized for situations where you want your data to be located close to your compute. Right? So it's a single location. You can put your compute right next to your regional data, and away you go. Low latency access to that data. Multi-regional data is very appropriate for data that you need to geo-replicate, make available in lots of different locations. Very, very well supported for either archival use cases or for content serving and delivery, where the availability of your back-end data is very high, but you don't need to combine the data with compute. And then dual regional is kind of when you want a little bit of both. Right? You want certainty about where your data is located so you can pair it close to compute, and you also want geo-redundancy. So you want disaster recovery or a backup site where you can move your workload processing to that other location and still keep it close to your data. Graphically, if you think about four objects, you can think about each type of object having flexibility in different ways. Our blue objects are regional objects, right? So our regional objects are, our green objects are regional objects, which are located in a single region. Our blue objects are dual regional objects, which are replicated across 2 specific regions. And our multi-regional objects, indicated in red, are each replicated in 2 regions, but we choose which 2 regions for each object. Right? So we guarantee the data is in 2 regions, but you don't get to control which regions that data is specifically being replicated in, except for the constraint about it being in Europe or in the United States or in Asia. So one of the things that we introduced or announced last year is our new archival storage class. This is really targeted for your data that is really, really going to be cold, right? Data that you're going to access relatively very infrequently. This is often your tape archives, data that you have no particular desire to access, but you need to retain for various purposes. Often you combine your archival data with bucket lock to really guarantee that that data is being retained. The archival storage class is going to be made available very, very shortly. And as you can see, it just adds a new tier of access, lower cost for storage, with higher cost for access. And it is also available with our different location options. Right? So it's available regionally, dual regionally, or multi-regionally. So you have a lot of flexibility with GCS to choose the storage class which is really appropriate to your hotness and your location constraints. Now, one of the other nice things about all of this is that you can tier data between the hot tier and the cold tier. And the nice thing about this is that tiering no longer changes the location of your data. So if your data is dual regional and you tier it from hot to cold, that data will stay in that dual regional location. So again, we often hear from our customers that they really care about the location of their data, and they care about the hotness and coldness, and they want those decisions to be separate and not tied together. And so that's a new capability in GCS that really allows you to really control location and hotness independently. OK, so that's an overview of storage buckets and storage locations and hotness and coldness. As you can see, GCS really provides you a lot of flexibility around how you control location and hotness and coldness. Let's turn our attention now to content serving and the different ways that you can serve your content from GCS to your end users. There are many different options for accessing GCS or serving directly from GCS. First one is direct serving. Your clients can choose to simply access GCS objects directly via our edge and receive it from the back end. You can also choose to use use our cloud CDN. You could also choose to build a custom edge, often in GCE or GAE, or you can take advantage of an independent third-party CDN with an edge shield. Let's talk through these different options and the choices that are involved. So, direct serving. With direct serving, you are simply accessing GCS objects directly from the back end. Google automatically provides you edge caching for your data. So as you access the data, if it's hot data, we will cache it at our edge, and that saves you latency. And gives you that access to that data through our global network very quickly. A cloud CDN allows you to have even more control over how edge caching works. So with a cloud CDN, you have the flexibility of controlling the domain name. You have the ability to control which data is served from the edge. You can control static data versus dynamic data. And you actually, because the data is cached in cloud CDN, you can save on egress fees, right? So your data is not being served from GCS, and because it's only being served from Cloud CDN, you're reducing your egress fees. So that's your second option. Third option is to build a custom front end, right? And we often see this pattern used when you need to do some pre-processing of GCS data before you make it available. So often you might have a process that's running in GCE or in Google Application Engine, and that process is receiving the data coming out of GCS, is doing some kind of processing of that data, and then serving it up to the edge. Often you might actually combine a front-end, custom front-end with a CDN, right? Because your CDN will now access that custom front-end in a very specific location and reduce latency by simply allowing you to keep the data in a single region. Sometimes you might want to use a third-party CDN. Many of our customers use a third-party CDN and use an edge shield to really prevent data or reduce their egress costs against GCS. Often what happens is you've got some piece of data that suddenly becomes very hot, and an edge shield can basically pull that data out of GCS, save you the egress fees, and allow you to serve it directly from your own cache. Okay? So you've got a lot of different choices for accessing or serving data from GCS. We've seen all four of these patterns used by different customers, depending on how they want to balance performance, complexity, and latency. OK, so we've talked about content serving. Let's spend some time now talking a little bit about data analytics. Now, data analytics is all about being able to access your data quickly, process it, and get insights from that data. And as I mentioned, features like consistent listing, features like our fast network, really give you a lot of flexibility in how you really build analytics pipelines using GCS as either an origin or a destination store for your data sets. So let's talk a little bit about source data. Typically, you're ingesting your source data into GCS from a variety of different pipelines. It might be coming from on-premise. It may be coming from your applications. It may be your logs. It may be a sensor. And typically, that source data is going to get accessed by a compute node. Right? You're going to be doing a lot of scrubbing and cleaning and sorting and organizing of that data. Typically, we recommend putting your source data into a regional bucket in order to ensure that it has high performance when combined with your compute node. Now, your compute nodes are going to basically form a data pipeline. They're going to pull data out of your source. They're going to do a bunch of processing of that data, step by step by step. And then eventually, they'll deliver a set of output data. Well, what do you do with your intermediate results? You can certainly put your intermediate results back into GCS. That works great, and a lot of folks do that. But if you really want high performance, especially as you're moving data back and forth between processing nodes, often you might choose to put that intermediate result inside a persistent disk or inside local SSD. Right? Really caching that data so that different compute nodes can process that data, or different processing jobs can process that data together. Your staging data, your side-loaded data could come from any source. It doesn't really matter. Usually, you're not pounding on that data that hard. Right? So you don't really need to rely on high performance. Obviously, a regional bucket might be most appropriate, but you might be serving it out of a multi-regional bucket as well. And then finally, your destination data is really all about how you're going to use it. If you're going to be taking that destination data and serving it up, maybe you'll put it into a multi-regional bucket. If you're going to be pulling it into BigQuery or a data warehouse, a regional bucket may be just fine. Right? So it really depends on what you're going to do with that destination. Right? So sources in regional buckets, your side-loaded data in a variety of places, your intermediate results in persistent disk or local SSD, and then your final data in typically either a multi-regional or regional bucket, depending on what you're going to do with it. OK, I mentioned consistent listing as a great feature of GCS. This makes GCS a perfect backend for Hadoop workloads. And so if you are interested in Hadoop, we have a product called Dataproc, which is a managed Hadoop cluster. You can bring up a Hadoop cluster in 90 seconds or less. We have a connector that points your Hadoop cluster directly to GCS. So you simply change your URL to indicate that it's a GCS URL, and away you go. Your data will just work. And a lot of our customers are really using this at scale to really manage their pipelines. Now, a couple of tips if you are deciding to run Hadoop workloads out of GCS. It tends to be good to turn off configure your Hadoop workload to not do directory moves. Right? Remember, directories are really just a naming construct in GCS. So if you're trying to do an atomic directory move, that's really moving a lot of objects around. So you don't want to rely on atomic directory moves as a feature. Also, GCS tends to do really, really well with large objects. And so for smaller objects, so if you can manipulate larger objects, that's great. And if you do need to do a lot of small object manipulation, you'll often want to parallelize your access to GCS. OK, so we've talked about different ways of using GCS to really build your data pipelines and where to store your data. But rather than taking my word for it, let's learn about how GCS is being used in real life. There are lots of key industries that really rely on data analytics in a variety of different ways. And no industry is more interesting than gaming, where you need to get access to real-time information about players and the games and how the game is performing. So today I'd like to introduce Polina Vasiljeva. I'm sorry. She will pronounce her last name. I had it right. Can't do it on stage. From King, who will walk you through how King is using GCS and the rest of Google's toolkit to really manage its data pipelines. Thank you.
Thank you, Sandeep. My name is Polina Vasiljeva. Yeah, so quite a complicated last name, but there we have it. I'm a data engineer at King. And for those not familiar with King, King creates and publishes free-to-play mobile games. We're part of Activision Blizzard, and our biggest and most famous game franchise is Candy Crush, which I'm sure many of you in the audience have heard about. Today, I'm going to give you a brief overview of how we use Google Cloud Storage in processing data generated by over 200 million monthly active users playing our games around the world. In 2018, we moved our data warehouse at King from on-premise Hadoop to BigQuery, and all of our data processing now runs in the cloud, so in GCP. On a typical day, we process 100 billion game events. This amounts to, on average, 1 million game events per second. However, we have spikes going all the way up to 4 million per second at peak activity times. Our data scientists across the company and data analysts have access to 4,000 live tracking events. So this means that every day we populate 4,000 different tables in BigQuery. And we also store 15 petabytes of data across GCS and Google BigQuery. So what part does cloud storage play in data analytics at King? Well, one can say that data analytics at King begins and ends with Google Cloud Storage. So let's imagine you're playing one of our games, and let's say you're playing Candy Crush. And so while you're playing Candy Crush, you match candies, maybe you connect with your friends, maybe you buy a booster. All these actions generate game events, which are stored as compressed log files on our game servers, which run on-premise. Throughout the day, we copy about 4 terabytes worth of these compressed log files into a regional GCS bucket, which is the entry point for our data processing, because this is from where our cloud data flow jobs can read the files, parse the data in them, and output it into BigQuery. Once we've concluded data processing for a day, we extract the daily partition from BigQuery into compressed Avro files, and this amounts to an additional 5 terabytes worth of data. And these files, they can be used by us, so data engineering teams, to reload the data into BigQuery, and they are also used by data scientists who run their analytics workflows on Cloud Dataproc. We only keep most recent 30 days of files in these regional buckets. So the Avro files also go into a regional cloud storage bucket. And everything that's older than 30 days, it's automatically archived in cold line buckets. So this is part of our data retention strategy at King. We store our data in Europe. So our data location is in Europe, but the buckets are located in different regions. And we do that for disaster recovery purposes. But beyond using GCS for file storage, we also use it as part of our hybrid cloud strategy, bridging the gap between on-premise and GCP. So due to firewall restrictions, certain internal servers and things like company GitHub and Artifactory are not available from within the cloud. And so we solve this accessibility problem by syncing these resources that we need in order to run our data pipelines to GCS. From there, Cloud Dataflow and other data pipelines we have running in Cloud Composer can easily access them. In addition, some of these data pipelines that we have, they publish build artifacts and things like metadata that ultimately need to be made accessible on-premise. So once again, here we use cloud storage again as an intermediate, where we first publish this data into cloud storage. And from there, consumers on both sides, so consumers on-premise, but also in the cloud, can easily access it. And this concludes my short introduction to how we use cloud storage at King in order to enable our data processing. Thank you very much.
Thank you. I'm so sorry.
Thanks. No, sorry.
Thank you, Polina. As you can see, using GCS to manage large data sets, manage for hotness and coldness of your data set, and get very fast access for running large data processing pipelines are intrinsic values. But the question is, how do you really do this at scale? How do you really build your application and build your pipeline so they can get high performance, high reliability, and scale to large volumes of data. Let's spend a little bit of time talking through a few techniques, a few tricks, and a few pitfalls to watch out for as you're building your applications. So let's start with a few performance rules of thumb. So as you're accessing data from GCS, roughly speaking, you want to expect about 100 milliseconds for cold reads, about 100 milliseconds of read and write latency for a small object. And as you're accessing data and throughput, you can expect 400 and 600 megabytes per second of throughput, right? Again, taking advantage of Google's fast network to give you very fast access to move the data around. So what does all that mean? Well, if you're really optimizing your access to GCS, you're going to want to take small objects and parallelize them, right? Move them in and out of GCS in parallel so you're not waiting for reads and writes to complete, right? Take advantage of filling that network bandwidth as quickly as you can. To the extent you can, favor using large objects, right? Take advantage of that throughput to really deliver that access, right? And obviously, what you want to do is take advantage of that amortize that time to first byte latency across as much access as you can. So there are lots of different ways that you can read or that you can write data into GCS. Simplest thing you can do is do a straight upload. A second model is to be able to do a resumable upload. A resumable upload is one where you simply set up the upload, tell us that you're about to do an upload that's resumable, and then you basically start uploading chunks of data, kind of continually resuming the upload until you're done, and you signal that you have uploaded all of the bytes. A third model is to do parallel uploads, where you upload all the chunks of your file in parallel, and then you tell us to construct a composite object that pulls all of those chunks together. And you can actually compose composite objects and build larger and larger objects that way. So there's three very different models. Direct upload, single object upload, great for small and medium-sized objects, really, really simple, it just works. But sometimes you've got very, very large objects. Maybe your network is a little bit slow. It's going to take a long time to upload. Maybe you're worried about the reliability of your network. This is where resumable uploads makes a lot of sense. Here, if there's a failure during your upload, you only have to restart that chunk that you're in the middle of uploading. You don't have to restart the entire object. Now, the downside is that there's an additional set of calls that you have to make to set up and complete the upload, right? Especially that initial setup is one round trip before you can begin to upload your data. So this works really well when you have very large objects and can amortize that cost of the initial upload or that initial RPC over the lifetime of that complete upload. As a general rule of thumb, I like to recommend that you chunk your data into 30-second chunks. So kind of figure out how much bandwidth you have and divide that up into 30-second chunks of uploads. That way, if the network goes down or a request fails, the maximum loss that you're going to experience is 30 seconds of upload time. Okay, so a good general rule of thumb. That 30 seconds is big enough that you can actually amortize the cost of your initial resumable upload setup and still have fairly small amounts of loss if there's a network connection event. I kind of recommend using parallel uploads as a last resort. They're particularly useful if you have very, very large networks, very, very large objects, or networks that have very high bandwidth, but they're also very high latency, right? So if you really can't fill up the pipe because the latencies are long, then parallel uploads make a lot of sense, right? So they're kind of a special case, but a very useful one when you need them. Let's talk a little bit about retries, right? So a typical problem that you run into with accessing GCS over the internet in particular is that stuff sometimes goes wrong, right? Sometimes you have to retry. Simple model, best practice is to do an exponential backoff on your retry, right? So you're going to try, and if it fails, you're going to back off, do an exponential backoff, and then try again. Now, there are two wrinkles. First question is, when you retry, do you want to retry the exact same operation, or do you want to change it? Right? For example, sometimes it might make sense that you retry the exact same operation to a full upload of a full object. Maybe what's happened, though, is the network has become flaky, and you're better off actually restructuring your retry to do it in smaller chunks. So sometimes what you're retrying may not be the same request that you tried initially. The second dimension is what's the deadline? Right? This is a question of how long do you wait until you deem that the retry or that the request has failed. And again, sometimes you want to use the same deadline each time, and sometimes it may be more appropriate to just give the system more time if there's really a spike in network or a slowdown over the internet or some other issue in the back end. A longer deadline might be a more appropriate approach when you're doing exponential backoff. Right? My point is that you don't have to do the simple thing and just retry everything over and over again in a tight loop. Exponential backoff, possibly restructuring your retry, and possibly changing your deadlines are all techniques to kind of give you more flexibility and chances of increasing the reliability of your access. One more dimension that is worth exploring, GCS in the back end automatically takes care of doing failover and retries across different metadata and data storage nodes. Right? So if we have a problem internally, then we'll take care of spreading load and moving things around in order to accommodate for those challenges. But if there's an issue in the front end, obviously there's not much we can do about it. And so sometimes if you may need to retry your request by pushing to a different front end. And so that allows you to have much more flexibility to deal with systemic failures or problems that might be happening either on the internet, in the network, on the route. OK. We talked a little bit about deadlines and the question of how long do you wait until your request fails. And this is a tough trade-off, right? Because sometimes if you're aggressive, if your deadline is short, you might get some false positives, right? You might fail a request even though it was just taking a long time. But you increase the likelihood of being fast. You might just waste a lot of work. Long deadlines reduce the likelihood of false positives, but you might, but if there is a failure, you're waiting a longer time in order to retry. Right? So there is a trade-off between sort of the throughput of your system and how much effort and bandwidth and transactional volume are you wasting. So there's a third approach, which is sometimes appropriate, which is really a hedged request. This is a request where you're going to make a request of a deadline. You know what the 95th percentile is of the performance, and if you see that something looks like it's exceeding 95th percentile, you're going to proactively retry. So this is branch predicting a retry ahead of the actual failure. So here's how this works. You start attempt number 1, and if the elapsed time has exceeded the 95th percentile, then you'll initiate a second request. Right? So roughly 5% of the time, you might actually retry. You'll be retrying. Now, there's a couple of different scenarios. In the case that that first request is simply taking a long time, attempt 2 will succeed, in which case you can go and cancel request number 1. Right? In this case, your performance will be faster than if you'd waited for request 1 to complete or fail. So you get the higher throughput. Now, scenario number 2 is where you initiate the hedged request, but in this case, item number 1 actually succeeded. In this case, you just cancel request number 2. Right? And what's really happening here is that you have just a long latency request You just didn't know it happened to exceed your 95th percentile, and you were just better off waiting, but you couldn't have predicted that. So a hedged request can be used to really manage your long tail of performance if you have a long tail, where you can actually use those requests to basically try and shorten that tail and bring it in. Some other retry best practices are to make sure that you are paying attention. We talked about exponential backoff. The other thing is to really pay attention to idempotency. Like, one of the challenges that we often see applications take is they do retries. They don't realize that both requests are now in parallel. The first one hasn't actually failed, right? And so it might actually succeed eventually. So here's an example of a very simple transaction model where you've created an object, the object has been created successfully, you delete it, and then you go back, there's a timeout on your deletion, you go back and try again to delete. Let's see, whoops. There we go. So here's a very simple structure. You create an object, you delete it, and then you create a new object with the same name, it's a new version, and then you delete it. If everything works perfectly, this is really great. The problem is, of course, if one of these requests gets lost or is sitting in the network for a while and takes a little longer. So here's an example of what might happen, right? You might create an object, initiate the request to delete, it times out, you send out that request a second time, and now that new deletion might delete your first object, it might succeed. You create your second object, and then the original request happens to come along and delete your second object. So you've just lost your second object unintentionally because you had two requests running in parallel that kind of completed out of order. The best solution to this problem is to be a little bit more explicit about how you make your request. So don't just say delete the object. Be specific about which version of the object are you actually trying to delete. So in this particular case, request that you delete version 1 of the object. So if that deletion request happens to show up late, it's not going to affect version 2 of the object. So being a little bit more explicit about what you're trying to do allows you to deal with duplicate requests trying to do the same thing in parallel, right? Simply saying a delete without a version allows anything to get deleted, even if it happens to have been recreated. All right, let me talk a little bit about performance. And to do that, let's talk a little bit about what's going on under the covers inside GCS. So I mentioned that we provide consistent listing, right? Consistent listing meaning when you write an object, you can get a listing of your bucket or a listing of your objects, and that recently written object will immediately show up, right? It's very consistent, just like a file server. So the way we do that under what we're doing under the covers is we are sharding your bucket across different nodes based on the load, right? So, if so we start out by basically taking your namespace, dividing it up across nodes, and then if there's a lot of heavy access to a portion of a namespace, we'll start splitting and joining those nodes, right, in order to give you consistent performance. Well, one of the reasons we do it this way is to give you really good performance for consistent listing, right? Because you want to make sure that we can give a very quick access to the list of objects that is currently in that bucket. So what we're doing is we're splitting the node. So this is a case where the middle part of the alphabet is hot. We're splitting it in order to reduce the load on that shard. Well, this works really well most of the time. But there are situations where you can essentially laser or really force heavy load into a different piece of the namespace, right? And when that happens, you're going to cause excessive splitting and joining of these nodes, which actually will impact your performance. Now, most of the time, you don't have to worry about this. But if you do have very heavy load, and as a rule of thumb, think about 1,000 writes per second or 5,000 reads per second, then you want to pay attention to how you're using the namespace. So let's talk a little bit about what's really going on and why this matters when you're dealing with an analytics workload. So if you've got two shards, and you're starting to do, for example, a sequential access or lots of sequential access through this namespace, what's going to effectively happen is we're going to start seeing this as hotspotting on the shards. We'll split the shards up into smaller pieces in order to give you uniform performance. Right? The problem is that when you want to do a consistent listing, we have to then look at all of these nodes in order to give you that information. Right? So there's a cost in order to give you that to provide the consistent listing, and it gets worse as more and more of these shards get created. Right? So we're trying to load balance, and that's going to impact your listing performance. So how do these sequential things show up? Well, they come up all the time. Right? You might be numbering your objects or naming your objects based on the month, day, and year, or year, day, and month that it was created. Right? It may just be an alphabetical order or sequential order. Right? And so it may just be timestamps. So there's lots of things that you can do to simply manage your namespace. Right? You might just reorder the fields in your object names in order to basically spread the load more evenly. Right? So instead of putting it in year, month, day order, maybe you do day, month, year order. Or you put the type of file at the beginning in order to break the lexicographic ordering of your object names. Right? You might apply a hash to your namespace in order to basically spread the load in multiple shards. The important thing is that this only matters if you're doing heavy load, heavy reads, heavy writes across your namespace, or you're lasering particular parts of your namespace where you really don't want to force us to have to shard that bucket. Okay? So the key is to break your load up so you spread it across multiple prefixes if you're under heavy load. All right, so let's wrap up. We've talked about a lot of different things today. We've talked about the fact that GCS is very well suited for a variety of different workloads, whether it's content serving and delivery, analytics, or archival. We've talked about the fact that storage classes give you a lot of flexibility to really control your data based on location, based on performance characteristics, based on hotness and coldness. We've seen some real-life examples of how you can apply content serving and delivery and data analytics in your GCS data, whether it be directly serving or using CDNs or using edge caching for content serving, or using Dataproc, BigQuery, data pipelines, and manage and consistent listing in GCS. You've seen a real-life example of how data analytics can be used to manage large quantities of data in the gaming industry. My thanks to Polina for coming up and presenting that information. And then you've seen a few tips and tricks for really optimizing how you use GCS for performance, for reliability, and for scale. With that, I'd like to thank you so much for your time today. Polina and I will both be here to answer questions right after the talk. And please enjoy the rest of the show and have a wonderful experience. Thank you.